Hello everyone, I am Zhangliang Song, a third-year direct track PhD candidate at Tsinghua University, working under the supervision of Associate Professor Lu Xing. Today, the topic of my presentation is geophysical mass flows over complex micro-topography, bridging grand-scale mechanics and continuum models. Granular flow is a widespread phenomenon, from volcanic eruptions to submarine landslides. Despite varying scales, they all exhibit remarkable hypermobility. Understanding this behavior is crucial for hazard mitigation. Natural terrain is inherently multi-scale, while large-scale features are often simplified as mere slow variations. The impact of the particle-scale micro-roughness is frequently overlooked. However, these micromechanics have a significant impact on macro-scale mobility. They dictate the basal resistance and ultimate runout of the entire flow. Conventionally, large-scale simulations treat granular materials as ordinary fluids using conventional boundaries. This oversimplifies the interaction at the base, as granular matter has significant particle-scale dimensions. Although recent literature suggests that Navier-type slip condition is promising, implementing this micromechanical insight into a robust continuum framework remains a major challenge. To address the research gap, the focus of this presentation will cover three key steps: investigating flow-based micromechanics through DM simulations, develop a roughness-informed boundary condition, and finally, implement and validate it in a continuum framework. First, we need to define particle-scale geometric roughness. For granular materials, it represents the degree of boundiness during motion. As this stroboscopic image shows, using smaller base particles makes the flow much smoother. Conversely, increasing the spacing between base particles makes the motion much bumpier, and if the gaps are too wide, the flowing grains simply get trapped and become part of the base itself. To quantify this, we use the geometric roughness index Ra, defined as the ratio of the available void area to a reference curvature area. As shown here, we generate base topographies ranging from a smooth Ra of 0.05 to a highly bumpy 0.55. With the base roughness defined, we simulate the granular column collapse on both horizontal and inclined planes using the DM method. However, DM only gives us discrete particle data, so we applied a coarse-graining method. It smoothly translates individual particle information into continuous fields, which is the foundation for deriving our new boundary condition. Now, looking at the overall flow characteristics, we simulate column collapse over different base roughness. We can see that as the geometric roughness increases, the basal resistance becomes stronger, which significantly decreases the final runout distance. To quantify this relationship, we plot the normalized runout distance against the geometric roughness, starting here with the smooth case, then include the rough case. And by plotting all intermediate cases, we review a nonlinear trend. The runout distance decreases as the roughness increases, eventually reaching a plateau. To understand this runout trend, we examine the internal kinematics. Our primary focus is at the base. As highlighted in the red box, we systematically extract the basal slip velocity and shear rate, separating the dense core from the dilute front. As we can see on the left, for the smooth case, the basal slip velocity and shear rate exhibit a highly linear relationship. The slope of this line directly defines the slip length Ls from the kinetic theory for granular flow. When it comes to the rough case, this slope drops significantly, and by filling in all the intermediate cases, we obtain a systematic curve. The slip length decreases as the roughness increases. This proves that micro-topography strictly controls the microscopic basal slip. But we must ask, is this relationship universal, or does it change with different flow conditions? To test this, we varied the inclination angle of the slope, changed the initial aspiration of the granular column, altered the particle diameter, and even enlarged column volumes. Remarkably, despite these different microscopy setups, all the data flaps perfectly onto a universal master curve. These exciting findings proves that the slip length is an intrinsic property of the boundary, dictated strictly by the roughness and is independent of the flow states. To investigate the microscopy essence, let's look at the collision angles. First, this animation shows the bottom contact layer and its real-time angle distribution, keeping the same roughly throughout the process. Then, as the red dot moves along the trend line with varying roughness, notice two features. The massive collision angle increases, and the distribution shifts from a single peak to multiple peaks. This demonstrates that the dependence of the slip length on base roughness fundamentally originates from grand-scale particle collisions. Now, we finalize our general basal slip law. First, we found that the maximum collision angles across all roughness are in perfect agreement with the theoretical geometry limit. This confirms that the basal slip is fundamentally locked by the base geometry. Furthermore, these collisions exhibit three distinct distribution types: smooth, medium rough, and rough. Each region represents a unique microscopic interaction. Driven by these states, we can finally propose a three-stage, piecewise slip law. With our universal slip law now fully established, we face the next challenge. How do we bridge the gap from this local kinematic relationship to a large-scale continuum model? For the continuum simulations, we use the Basilisk solver, whose established foundation already includes the standard mu-I rheology and general boundary conditions well agreed. Then, our key contribution is adding the new Navier slip length model into this framework. Here comes the results from the continuum simulations under different boundary conditions with the same setup as DEM. As seen in the second row, our proposed slip length model perfectly reproduced the DEM results outlined by the red curve. In contrast, traditional no-slip and Coulomb boundary completely fail to capture the deposition morphology. To push this validation even further, we test our model on an inclined slope of 10 degrees. As highlighted by the red dash box, our newly proposed slip length model once again perfectly reproduced the DEM profiles for both horizontal and inclined cases. But more importantly, please look at the right panel. We systematically plot the final runout against all the geometric roughness. The predictions from our continuum model align well with the DEM for both inclinations. This firmly proves that our roughness-informed boundary conditions is highly robust and applicable across the entire roughness spectrum. To draw a conclusion, this research established a multi-scale modeling framework. As shown here, we start from the micro-scale geometric roughness, then bridge the gap by deriving the piecewise basal slip law. Finally, we implement it as a Navier slip boundary condition in the continuum model. This framework allows us to accurately predict large-scale flow mobility over arbitrary base roughness, and this work is under review in Computers and Geotechnics. Looking ahead, we are applying this model to more complex inclined deposition morphologies. As a quick sneak peek, whether the granular mass completely deposits on a slope or just flow away, it actually depends on this geometric roughness. This exciting follow-up work now in preparation for geophysical research letters. And that brings me to the end of my presentation. Thank you for your attention.